Okay, so in the last video we talked about the concept of energy, at least we introduced the concept of energy, and we kind of left off talking about this. Now, um, just to recap really quickly, this unit is mainly going to focus on mechanical energy, which includes kinetic energy and different types of potential energy. And we will come back to energy later on, but I do want to remind you that energy, the symbol for energy is a capital E. We use subscripts to denote different types of energy. The SI unit for energy is the joule, and all forms of energy are scalars. Okay, and so before we get back to talking about energy, we're going to introduce the concept of work. Now, work calculations tend to not be super complex necessarily, although there is some math stuff you need to be aware of. Um, but it's really, really important, like anything in physics, that you understand the concept of work. Okay, because there's lots of problems that will ask you to do calculations, not necessarily using an equation, but just using the concept of what's happening in the problem. Okay, so pay really close attention, make sure you take good notes, and focus on the concepts. Okay, so work in everyday language might mean like a job you do, or working on an essay or something like this, but work has a specific meaning in the context of physics. Okay, and so the concept of work is this. Work is basically a mechanism through which energy is transferred to or from an object. Okay, so work refers to the transfer of energy to or from an object by a force. Okay, so some force acts on an object, and that force could possibly add energy to the object, or it could remove energy from the object. Okay, so for example, if there's a football and it's just laying on the ground, and I kick it, okay, I'm doing work on the football. I'm transferring energy from my body into the football. Okay, the football gained energy because of the work that I did. When you push on a chair and the chair slides across the room, okay, that's an example of work being done. That is a force acting to transfer energy to the chair. When your car goes to a stop, let's say you're driving along the highway, you run out of gas, okay, um, slowly what's going to happen is your car is going to stop because there's friction in the road. Okay, so in that case, friction is going to actually remove energy from the car. It's going to take energy away from the car, and so that is also an example of work being done. Okay, so these are all examples of work being done. Anytime a force transfers energy to or from an object. Okay, and typically we talk about the work done by a specific force. And so you can have an object that has like 3 or 4 different forces on it. We've seen that before. And each one of those forces might be adding a little bit of energy or taking energy away. Okay, and so you could have, 20 forces acting on one object, some of them um, increasing the energy of the object, some of them decreasing the energy of the object. Okay, so the concept of work refers to the transfer of energy to or from an object. Okay, so keep that in mind as we're going and doing some examples later on. Okay, now here are some facts that you just need to know about work. Okay, fact number 1, work is a scalar. Fact number 2, work is done when a force acts on a moving object. Okay, now there is an equation that we're going to learn for work. Um, Please note that this equation has a limitation. Anytime you're doing anything in physics, you have to understand what are the limitations of this equation. So for example, when we talked about the constant acceleration equations, I was very clear that those equations only apply in the condition that you have constant acceleration. Just like the constant velocity equation, s equals v times t, that only works if you have constant velocity. Okay, so this equation I'm about to tell you for work only works, haha, for a constant force. Now, if the force is not constant, that's actually when you need to start using calculus in that situation, but we're not going to worry about that in this case. Okay, so if you have a force which is constant, then we can calculate the work done by the force through this equation. Okay, we say W, capital W for work, is equal to F S times cosine theta. Fs cosine theta, where F is the force in question. Note that is a vector, so I put a little arrow on top of it. S is the displacement of the object, and we've seen displacement before, that is also a vector. Now, notice that work is a scalar. Work is not energy, but it does have the same units of energy, which is the joules. because it's a transfer of energy. So even though, you can't possess like 10 joules of work, you can do 10 joules of work on an object. So work is a scalar, but if you look at the equation actually has two vectors in it. And so there's a way to multiply these two vectors to get a scalar, which is what's happening here. And so even though work itself is a scalar, you still kind of have to worry about the vector nature of the force and the displacement. Because notice that in the equation you have cosine theta, where theta is a very specific angle. Again, make sure you take good notes here. Theta is the angle between F and S. Okay, and it's really important that you understand what theta is, because sometimes you'll see they give you an angle in the problem. Just because they give you an angle doesn't mean that you use that angle. Okay, you have to really think about what that angle in the equation represents. It is the angle between F and S. Okay, so if force is a vector, that means you can draw it as an arrow. It has magnitude and direction. S is displacement. That's also a vector. That also has magnitude and direction. Okay, so if you were to draw out the force arrow, the force vector, and the displacement vector, there is going to be an angle between those two, right? That's what theta is in the equation. Okay, theta is the angle between the force and the displacement vectors. Now, what are the units for work in terms of SI fundamental units? Okay, so in the last unit, we kind of started talking about how do you find the units for something? Okay, well, you find the units for something by taking an equation and plugging units into the equation. Okay, so let's take a look at the work equation and see if we can figure out the units for work in terms of SI fundamental units. Okay, cosine theta doesn't have any units, that's just going to be a number. Okay, so for the sake of units, let's just ignore the cosine theta part because it doesn't matter as far as units go. Now, what are the units of work? Well, the units of force are newtons. The units of displacement are meters. And so the SI fundamental unit for work is just Newton meter, not newtons per meter, Newton meter. Now, for some reason, people didn't like that, and so they gave that a name. They called that joule. Okay, so 1 Newton meter is equivalent to 1 joule. Okay, but that's how you would um, take like a quantity to like work and figure out what are the fundamental units that make up that quantity. Okay, so 1 joule is 1 Newton meter. You basically take the equation, you plug the units into the equation, and we've seen that before. Okay, so pause there, make sure you have this added to your notes. Okay, so remember that work is done by a force when that force transfers energy to or from an object. Okay, now even though work is not a vector, okay, it doesn't have direction, that doesn't necessarily mean that it cannot be positive or negative. Okay, so work can be positive or negative. It's just that the positive or negative sign does not indicate direction, but it indicates something else. Okay, so when we talk about force being positive or work being positive, generally positive work refers to a force adding energy to an object. And when we talk about negative work being done on an object, we talk about a force removing or subtracting energy from that object. Okay, so what would an example of that be? So for example, if let's say you kick a soccer ball, okay, your foot is adding energy to the soccer ball, and then the soccer ball flies off. Okay, after a while, the soccer ball is going to roll along the ground. There's friction on the ground, and the friction is going to remove energy from the soccer ball. Okay, so in that case, your foot did positive work. The friction in the ground does negative work because it removes energy from the soccer ball. Okay, the most common example of negative work being done is by friction or other resistive forces like air resistance. That's not the only situation where you have negative work, but that is the most common. Okay, now I want you to think carefully for a second. I want you to look at the equation for work, Fs cosine theta, and I want you to try to figure out the situations in which the work done by a force is zero. For what situations will the work done by a force be zero? And I'll give you a hint, there's three possible answers, although one of them is maybe trivial. Okay, so see if you can figure that out. Okay, so the three situations where a force does no work is number one, if the force is zero. That's maybe too trivial, but that's true. If there's no force acting, obviously the force cannot do any work. Number two, if the object does not move. That is, if the displacement, wow, that is, if the displacement is equal to zero. What I'm doing here, by the way, in case you didn't figure this out on your own, is there's three mathematical terms in this equation. If any one of these is zero, then all of the work done is zero. The third situation is basically the situation where cosine theta is equal to zero. And so you might be wondering, okay, so I know theta is an angle. For what situations is the cosine of theta equal to zero? Okay, well, it turns out that cosine theta is equal to zero if theta is equal to 90 degrees. In other words, the third situation is if the force and displacement are perpendicular to each other. Right? Remember, theta is the angle between F and S. And so if the force and displacement are perpendicular to each other, that means that theta would be 90 degrees and cosine of 90 degrees is zero. Okay, and so these three situations are the situations in which the work done by force is zero, meaning that force is not transferring energy to or from that object. Okay, so pause it here, make sure you're taking good notes, and then we're going to do some example calculations. Okay, so example one. We're going to start off with a baby problem. We have a 100-newton force is used to push a box 5 meters across the floor. Calculate the work done by this force. Okay, well, so we have the applied force. The box moves 5 meters. Okay, and so let's just say, for the sake of simplicity, that the force is pushing the box in the positive direction. So that way, the direction of the displacement is also in the positive direction. Okay, so here's what the situation looks like. Here's a box. Okay, we could draw an FBD, but really the only force I care about is the applied force right now. The applied force, let's say, is going to the right. It doesn't matter which way it's going, but whichever way the applied force is acting is the same direction that the box is moving. So in other words, the displacement vector, I'm not going to put it on the FBD because it doesn't go there, but the displacement vector is also to the right because that points in whichever way the box is moving, that's where the displacement is. Okay, so Fs cosine theta. Very simple calculation. F is 100. The displacement is 5. What is theta in this case? Well, if F is to the right and S is to the right, the angle between those two vectors is 0. Okay, 0 degrees. And it just so happens that cosine of 0 degrees is 1. And so we have 100 times 5 times 1, which is 500 joules. Okay, so that is, for example, one very, very basic work calculation. Pause there if you need to look at it some more. What that means, by the way, is that this force that's used to push the box is adding 500 joules of energy to the box. Okay, so example 2. Example 2 says a 100-newton force is applied to a box which remains at rest. Calculate the work done by this force. Try to do example 2 on your own. Okay, well, if the box remains at rest, that means the displacement of the box is going to be 0 meters. So that means I can tell right away that the work done is going to be 0 because we have 100 times 0, which is immediately 0 because 0 multiplied by anything is 0. Okay, so this force does no work. Again, very basic, simple calculation question. Okay, so let's go to the next one. Example 3. Now we're going to mix it up a notch. Okay, it says a 100-newton force is used to push a box. Okay, so same applied force is used to push a box. This is my applied force. Is used to push a box with a mass of 10 kilograms, and it's pushed 5 meters across the floor. So very similar setup to what we've had before. As the box is pushed, the force of friction acting on the box is 30 newtons. So now we've got a lot more going on. That's going to be kinetic friction, by the way, because it's moving. Read what the question says. Calculate the work done by the force of gravity. Okay, so I want you to pause it there and see if you can do example 3 on your own. Okay, so this is one of those problems where it's a super easy problem as long as you're paying attention to what it is you're doing. Okay, the key here is that we're asked to find the work done by the force of gravity. And so let's take stock of the situation. We have a box, and there's, let's say, a few different forces acting on it. We've got Fg, we've got, Fn going up, applied force, blah, 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 and then let's say kinetic friction going to the left. Now, each of those four forces could possibly be doing work on the box. We were specifically asked about the work done by the force of gravity. Okay, so the work done by the force of gravity, work is Fs cosine theta, so that would be the force of gravity times the displacement times cosine theta, where theta is the angle between the force, in this case the force of gravity, and the displacement. Now, before you run off to calculate the force of gravity, which we could do because we have the mass, it wouldn't be hard to do, but we actually don't need to do that because guess what? The force of gravity is going down. The displacement is to the right because the box is being pushed to the right, so it's moving to the right. Remember, theta is the angle between the force you're talking about and the displacement of the object. Okay, so what angle would that be? Well, that would be 90 degrees. Look at that angle right there, 90 degrees. Cosine 90 is 0, and so the work done by the force of gravity is 0 joules. That's the answer to the question. Okay, so notice when you're doing questions with work, you have to read them very carefully. It's not enough to just say, what is the work done? You have to say, what is the work being done by this specific force? Okay, so Fs cosine theta, the work equation lets us calculate the work done by a specific force. Now, if I ask to calculate let's say, what is the work done by the applied force, then that would be different. Okay, and in fact, I think we might see it on the next slide. Okay, so pause there if you need to add that to your notes. Okay, so let's take a look at this. Example 4. It says a rope with a tension of 150 newtons is used to push a box. That doesn't make any sense. It should be pull. Pull a box 5 meters across the floor. As the box is pulled, the force of friction acting on the box is 30 newtons. And we're asked to calculate the work done by a couple different forces. Okay, so the situation, the FBD looks basically like what we had before, except you have tension instead of applied force, but that doesn't really change anything. Okay, so we got Fn, we got Fg. Let's say we got tension going to the right and friction going to the left, just like we had before. Okay, so the question says calculate the work by the 150 Newton force, calculate the work done by the force of friction, and then how much energy is added to the box overall. Okay, so pause it here and try to answer those 3 questions on your own. Okay, so the 150 Newton force is the force of tension. And so I'm going to write Wt, that is the work done by the force of tension. Now the equation for work is Fs cosine theta. And so I am going to multiply the magnitude of the force, which in this case is 150, times the magnitude of the displacement, which is 5 meters, times cosine theta, where theta is the angle between this force and the displacement. So this particular force is going to the right, which way is the box moving? To the right. What's the angle between right and right? Well, that's 0. Okay, and so if you multiply that out, you get 750 joules. Okay, so the work done by the 150 Newton force is 750 joules. Now, what is the work done by the force of friction? So I'm going to write WF, work done by friction. When I do this calculation, by the way, I'm putting 30 and I'm not putting negative 30. And somebody's going to say, but shouldn't the force be negative because it's going in the negative x direction? Okay, you don't need to worry about that in the equation because the cosine theta, the angle will take care of that. Okay, so you're only plugging the magnitude of F and the magnitude of S into this equation. Okay, so we have 30 times 5 times cosine. Now you have to think, which way is friction going? Friction is going to the left. Okay, to the left. Which way is the box moving? Box is moving to the right. Theta is the angle between the force and the displacement. So if the force is to the left and the displacement is to the right, that would be 180 degrees. And cosine of 180 is negative 1. Okay, and so this would actually be negative 150 joules. Now the last question, how much energy is added to the box? Here's the thing. The work done by the force of gravity is 0 joules. We actually saw that in the last problem. Okay, the work done by the normal force is also 0 joules for the exact same reason that the normal force is at a 90-degree angle to the displacement. In other words, cosine theta, theta would be 90 degrees if you were to calculate the work done by the normal force. So there's 4 different forces acting on the box, but 2 of those forces don't do any work. So if we want how much energy is added overall, okay, we give that term a special name. We call that net work. Just like you have net force, right? The sum of the forces, you have net work. That's the sum of the works being done by all the different forces. And so basically what net work is, it is, okay, so some forces are adding energy, some forces are removing energy. Okay, what is the overall result? Okay, so uh, the rope is adding energy to the object, okay, 750 joules. Friction is removing energy, that's negative 150 joules. Gravity and normal force do no work. So the answer to the last question is 600 joules. And so we would say the net work done on the box is 600 joules. Okay, so in other words, when everything is all said and done, even though there is friction, friction is taking energy out of the box, overall energy is still being added on the whole. Okay, so pause there, make sure you fully understand example 4. Okay, and this concept of net work, because we're going to keep coming back to this in the future. Okay, so I think on this slide, I basically talk about what network is, and I don't want you to freak out too much when you see network. I know like finding net force is kind of a pain because with net force you're adding vectors. With network you're not adding vectors, you're actually adding scalars. And so scalars are just numbers. They can be positive or negative, but you don't have to worry about components or anything. And so finding network is actually a lot easier than finding net force. Okay, so the net work on an object, W net, is the sum of the work done by the individual forces. Okay, so what you have to do is you have to find the work done by each individual force and add those values up. Okay, so one more example. Okay, so example 5 says calculate the work done by each individual force and then determine the net work done on this box. Okay, and so we're not given the displacement in the problem, and so I'm just going to make up a value. Let's say that the box is going to move to the right by 4 meters. Okay, so S, the displacement is 4 meters to the right, because otherwise you can't do the calculation. Okay, there are 4 forces acting on this box, and you should definitely be able to figure out those 4 forces on your own. We're asked to calculate the work done by each individual force and then determine the net work done on the box. So you should have 5 answers for example 5. I want you to pause it here and try to do example 5 on your own. Okay, so hopefully you were able to answer example 5 correctly. This is a very generic kind of work calculation problem. So let's start with finding the work done by tension. Okay, so remember, just for reference, work is Fs cosine theta. The key to doing these problems and getting the correct answer is understanding what theta is. Theta is the angle between the force and the displacement vector. Okay, so let's start with tension. We have Ft. And so the work done by tension would be equal to the force of tension, which is 150, times the displacement of the box, which in this case is 4 meters, times cosine theta, where theta is the angle between the force and the displacement. Okay, well, the force is like this, that's along the rope. The displacement is to the right, like this. And so theta is just that angle right there, which is 60 degrees. Okay, so that would be cosine 60. Okay, cosine 60 is 1/2, and so that's actually going to be 300 joules. Now, what about, the force of friction? What's the work done by that? Well, that would be the magnitude of the force of friction, which is 15, it's given right there, times the displacement, which is 4 meters, times cosine theta, where theta is the angle between the force and the displacement. So the force vector is to the left, okay? The displacement's to the right. I said that at the beginning. So the angle between left and right is 180 degrees. Okay, so again, you have to be really careful in these problems not to just see an angle and be like, oh, it's 60 degrees. Like, no, you need to understand what that angle represents. Okay, because theta here is not 60 degrees, it's 180 degrees. Cosine 180 is -1, by the way, and so that would be -60 joules. Now, I can tell you right now that Fg and Fn, Wg and Wn are both equal to 0 because both of those forces are going to be perpendicular to the displacement. Because if the box is moving to the right, Fg is down, okay, Fn is up. Up and down have a 90-degree angle to the right, okay, which means theta would be 90 degrees, which means those forces would do no work. Now, I do want to say, just for the record, it's definitely not true that gravity and normal force always do 0 joules of work. Okay, it just so happens in the problems we've done so far that that's the case, but that's not always true. Okay, so what is the overall net work done on the box? W net is equal to 300 plus -60 plus 0 plus 0, which is 240 joules. Okay, so remember, the net work done on an object you find by calculating the work done by the individual objects, the individual forces, and then adding up the work done by each force. Okay, so after watching this video, you should understand the concept of work as, a force adding or removing energy from an object. You should understand the work equation, the limitations of the work equation, be able to do basic calculations with the work equation, and then calculate the net work on an object. And we will see what we're going to do with that later on. As always, please let me know if you have any questions, and I'll see you guys in the next video.